Hello and welcome. My name is Kelby, and I will be presenting work Professor Gerald Wong and I have conducted on the flow physics of pedestrians and corridors. More specifically, we use particle simulations to see how social distancing may increase congestion in these spaces. So, the impetus for our research came out of seeing a lot of photos that look like this, and that look like this, where social distancing measures require the use of a heck of a lot more space. This is not a problem when you're in an outdoor space, like in the first photo, or when individuals can be assigned to a fixed location like a desk here in the second photo. However, maintaining social distance might become a problem when the students in this classroom and other classrooms need to get up and leave and go into the hallway during passing period, for example. Our question then is, how will the need for social distance affect pedestrian flow in corridors? And to answer our question, we decided to borrow a concept from traffic engineering. That concept is traffic fundamental diagrams. In a traffic fundamental diagram, the average velocity of a group of vehicles is plotted against the volume fraction of vehicles occupying a roadway. Intuitively, at a low volume fraction, the vehicles collectively will have a pretty high average velocity that is close to their desired velocity. Now, when the volume fraction of vehicles increases, the average velocity of vehicles will decrease. An analogous pedestrian fundamental diagram can be created by the same method as a traffic fundamental diagram, plotting the average velocity of a group of pedestrians versus the volume fraction of pedestrians on a pathway. A social distance factor was incorporated into our model so we can understand how social distance may impact the average velocity of pedestrians in a corridor. Our hypothesis was that an increase in social distancing and a social distancing factor will shift the fundamental diagram to the left, causing average velocity to fall faster for the same volume fraction of pedestrians. To model pedestrian movement in our simulation, we use the following equation, where force on each pedestrian is a function of three key parts. There is a selfish term that compels each pedestrian to move at a desired velocity. There is a random term that adds a tiny Gaussian kick to decrease stalling events. And there is a social interaction term that is in turn made of two different factors, two different terms. The first term deals with the physical particle contact. So this is pedestrians bumping into each other, and that's the near term. The far term deals with psychological forces of social distance, and that is set by the factor d naught. This term here, the u far term, set by this factor of d naught, is the focus of our work. Here is an example of what a simulation of ours looks like. We used lamps for the particle simulations, and then the visualizations here were created using Oviedo. Our simulations model a corridor counterflow where pedestrians, the red and pink particles here, attempt to move in their desired direction at the same desired velocity. I'll play the video here, and you can see that there is an initial scrum followed by steady channel flow. The average velocity of just the red pedestrians was sampled during steady channel flow to create the fundamental diagrams that we will see later. Here's a top-down view of the initial conditions of another simulation. The blue cylinders on the top and bottom are the walls, and they are fixed. The pedestrians and the walls are set on a hexagonal lattice, as you can see here. As you saw in the video, the red pedestrians want to move to the right, and the pink pedestrians want to move to the left. To change the volume fraction, individual pedestrians are removed from random locations within the initial lattice, as you can see here. They've been removed. The edges of the corridor are connected via a periodic boundary. In other words, when a red pedestrian exits off the right side, it re-enters on the left side, moving with the same velocity as when it exited, creating a continuous corridor. Simulations were run for a range of fractions, a range of volume fractions, and social distancing factors. A range of volume fractions from 1 to 0.05 was used to form a complete density spectrum that could be used in the fundamental diagrams. The range of social distancing factors was from 0.1 to 0.2. To give you an idea here, A factor of zero point 0.1 is physically equivalent to a pedestrian feeling an appreciable force at a distance of 1 meter away from them. And similarly, social distancing factor of zero point 0.2 is a pedestrian feeling that same appreciable amount of force against them, psychological forces against them, at a range of 6 feet away. So that's what we typically think about right now with COVID is that everybody's trying to keep these 6 feet distances. And so you would feel a force if somebody started to come within 6 feet of you. You'd be like, oh, I want to stay away from them. Finally, in order to increase our statistical confidence in our findings, for each fixed pair of volume fraction and distancing factor, multiple simulations were run with random seeds that would change the initial spatial configuration of the pedestrians. So you can see here we have two initial setups. They actually have the same volume fraction of 0.65, but in one we have a random seed here and we have a different random seed here. You can see that the initial spatial configuration for the pedestrians is different. All right, let's look at some results. So this plot shows the average velocity plotted against the volume fraction for a single distancing factor. As expected, the plot resembles a typical fundamental diagram, where as the volume fraction increases, the average velocity decreases. Here, we show the pedestrian fundamental diagrams for three different social distancing factors. As hypothesized, an increase in social distancing factor results in a shift left of the fundamental diagrams, meaning that the average velocity of a pedestrian will slow even with relatively low volume fractions, as you can see here. Here, we show fundamental diagrams based upon our simulations, spanning the full range of densities and all 11 distancing factors. Each data point on the plot represents an ensemble of 64 average simulations, and then the shading shows the associated 95% confidence interval. We can see a couple of striking trends here, most notably our hypothesis that an increase in distancing factor will result in a leftward shift of the fundamental diagrams holds up remarkably well. It is also pretty striking to see how drastically the average velocity drops for high distancing factors. To get a better look at the striking drop in average velocity that we just talked about, um, here we have plotted the volume fraction at which the average velocity of the pedestrians falls to 50% of the desired velocity for each distancing factor. At a high, or excuse me, at a relatively low distancing factor down here, at a relatively low distancing factor down here, the average velocity does not drop below 50% until a volume fraction of about 0.75. Whereas at a high distance factor, a volume fraction of only 0.25 will cause pedestrians' velocity to fall below 50% of their desired velocity. And that's pretty crazy. So with that, the main takeaway is that an increase in pedestrians' preference for social distancing leads to congestion, even at potentially relatively low densities, as we just saw. Now, moving forward, we hope to do a couple additional things with our simulations. We hope to create an empirical scaling relation connecting congestion to volume fraction, distancing factor, and corridor width. This would allow us, for example, knowing given the corridor width of this hallway in the photo, we could estimate how many people we could allow into this hallway before you might have a jamming condition occur because of social distancing. In the future, we also hope to create the simulation to have heterogeneous distancing preferences and target velocities. Now, this makes a lot of sense because in our simulation, we assumed that everybody had the same desired peak velocity and the same desired social distancing factor. And in real life, of course, that's not true. Some people are more wary of staying away from people than others. And of course, in real life, some people move a lot slower than others as their peak desired velocity. And my time on college campus has really shown me that difference in velocity, let's say. And finally, besides just corridors, we could test the simulation other kinds of confining geometries like T intersections, stairwells, or doorways. And with that, reach out and let us know if you have any questions. Thank you very much for your time. Bye.